Alright, in this example, I'm going to be illustrating the continuity test. So I'm going to be taking this piecewise function and I'm going to be testing to see whether it is continuous at a specific point. And we're going to be looking at where x equals 1. Now, in general, if I think about the continuity of the entire function, I'm really only worried about x equals 1 possibly being discontinuous anyways. Each of the pieces of my piecewise are graphs that would be continuous from negative infinity to infinity. So for less than 1 and for greater than 1, I don't have any x values that I'm concerned about in the domain of either of these. So we might have a discontinuity at x equals 1, but probably not anywhere else. In most cases, I'm going to specify exactly what point I want you to check, but it's good to be thinking about the entire picture of what this would look like. So let's test whether this is continuous at x equals 1. Now, we learned that for our continuity test, we need to show three things. First, we need to show that f of x can be evaluated at this specific value, x equals 1, and that exists. Second, we need to check from the right and the left side of x equals 1. We need to make sure that f of x has the same value. And third, we need to see that the value of the function that we got for f of 1 is the same as that left and right side approach. So first, let's start off with finding f of 1. Now, since this is a piecewise function, I need to look at specifically which part of my domain here I'm in, and I'd be looking at this first piece of the function where x is less than or equal to 1. 1 would be a part of that. So I'm going to plug in 1 to this first piece of my piecewise function and solve. 1 squared plus 3 times 1 minus 1 would give me 1 plus 3 minus 1. 4 minus 1 gives me 3. So that value exists. We can evaluate f of x at x equals 1. Okay. Second, let's see if from the left and from the right we are approaching the same value. Now, the nice thing about a piecewise function is that this less than or equal to 1 means to the left of 1, and this x greater than 1 means bigger than 1 would be to the right of 1. So I can basically look again at these two pieces separately and see as they get closer to 1, at 1, what would their value be. So let's look first at the left. From the left, that would be smaller than 1. We could plug in 1 to x squared plus 3x minus 1. Well, we just did that, and we said we got 3. Okay. From the right, that's for values bigger than 1. We can use 3x plus 4 to give us an idea of, as we approach 1, where are we headed. So 3 times 1 plus 4 would be 3 plus 4 is 7. Now, if you take a look, we were testing to see if we get the same value from the left and right side approach, and we do not. The left and right do not match. So we can already see that this is going to be discontinuous at x equals 1, and specifically, if I think about the type of discontinuity, this is going from coming in towards 1, 2, 3. I don't know exactly what it looks like, but I know that at 1 it's going to be up here at 3, and then when we switch to the next function, our line right here, it's going to start at 1, 2, 3, 4, 5, 6, 7 up here and then like shoot off somewhere there. I don't know exactly what the rest of the function looks like, but I see that this is a jump discontinuity specifically because it is at two different values from the left and from the right of 1.